Welcome. The unit is BMA1102 and that is Calculus 1. Our first topic is limits of functions. So that is limits of functions. And before we start talking about limits, at least we need to get to remember what a function is or what are functions. Basically, a function f is a rule or a correspondence. So that's a rule or a correspondence that assigns members of one set X, one set rather, to unique members of another set. So for example, if we have a set X and a set Y, and we pick our values for X, let's say from -3 up to 3, and you have the function f, or you have the function y is 2x plus 1. So what this function will do is that it will pick each and every member of this our set X. So if I write it like this, we have this is our set X. It has -3, 0 all the way up to 3. So what this function will do, so this is our function, what it will do is that for each and every member of X, it will assign them to unique members of Y. So for example, when you have X as -3, that would give us -6, plus 1, which will give us -5. And then when X is 0, I will have our Y as 1. And when X is 3, that would give us 6 plus 1, which will give us a 7. From here, we can see clearly that f is a function of x, y is a function of x rather, y is a function of x, and x is our domain, and y is our codomain. So y becomes the range if the members of y is composed of only the images of x. So then now we can talk about limits. So we start with the informal approach to limits, and generally we say that the number L, so the number L is the limit of f provided that we can make f of x as close to L as we please, merely by choosing values we need to introduce something here. So the number L is the limit of f. So this should be as x tends towards c. So there's something that important that is missing here. So the number L is the limit of f as x tends to c, provided that we can make f of x as close to L as we please, merely by choosing values of x sufficiently close to C, but not at C. So in that definition, there are two important parts of it. The first one is that we pick the values of x as we please, and our interest is to look at what is happening to f of x on the other hand. As we pick these values of x and we translate the values of f of x, what happens? What is the behavior of f of x? Is f of x tending towards a particular number, or what is happening to the values that we have for f of x? And you can see clearly here that you're saying that, but not SC. So when we are looking at the limit of a function, or when you're getting the limit of a function, the particular point is not very relevant in terms of what is the value of f of x at that particular point. And as such, the best approach to limits is generally to use a function that is not defined at a particular point, so that the implication is at that point where C, where you want to get the value of f of x, it is not defined, so there's no value. So for example, this is actually the graphical approach to limits, graphical approach to limits. And if you're talking about graphical, of course, a numerical must come in there, because it implies we look for tables, we draw the graph and all that. So if we start with this function, we are supposed to get the limit of this function as x tends towards 1. The function that we have is x cubed minus 1 over x minus 1. So we pick values. Our C here is 1. We pick values that are very close to 1 from both sides. That is from the left and from the right. Then we investigate what is happening to f of x as x tends towards this value and make a conclusion in terms of is f of x tending towards a particular value or is f of x, what is the behavior of f of x. So we have x, and then we have f of x. We can pick 1, 2, 3 values this side, and then we also pick 3 values the other side. So at this point we have our 1. We are really, the function is undefined at this particular point. So then this side, our direction is that, and this side our direction is this. So we are picking values that are close to 1 from both sides, from both values that are greater than 1 and from the other side where values are less than 1. So this side we can pick 1.1, 1.01, 1.001, 1.0001. So we can see that those values are moving closer and closer to 1. And this other side, we can pick 0.9, 0.99, 0.999, and 0.9999. So very clear from both sides, those values are moving towards 1. So when x is 0.9, our f of x is 2.710. When it's 0.99, it's 2.970. Then here it's 2.9970. Then 2.99970. Then on the other side, when x is 1.1, this is 3.310. Then 1.01, it is 3.030. Then 3.00, this is point here, 0030. Then 3.00030. So if we look at these figures for f of x, we can see that likewise the behavior of f of x as x is tending towards 1 is that f of x is actually moving closer and closer to the value 3. And if you look at the behavior of f of x on this other side, from the left hand side, we can see again that f of x is tending towards 3 again from this left hand side. So confidently we can say that the limit of this function as x tends towards 1 is actually 3. We can do a second example to this. We get the limit as x tends towards 2 of x squared minus 4 over x squared plus x minus 6. So same story again. I will pick values that are very close to 2 from both the left and the right, and then again try to investigate or make a conclusion in terms of what is happening to f of x on the other hand. So we pick x, we pick f of x. So we can pick 4 or 3 values. This side the same thing, we pick 3 or 4 values. So we can pick 2.1 here, 2.01, 2.001. This side we can pick 1.9, 1.99, 1.999. This can be our 2. We know that the function is not defined at that point. So then at 1.9, this will give us 0.79, 591. Then at 1.99, it will give us 0.7, 9959. This will give us 0.799959. And then from this other side, we have 0.8039. This will be 0.080039. 0.800039. So if we look at these figures, it implies that we can conclusively tell what value f of x is tending towards, because we see the trend. These values, this is not the closest that we are to 2, but we know that we can get closer to 2, and by getting closer to 2, we know what would be the reaction on this other side. So again, out of this, we can say confidently the limit of this function as x tends towards 2 is 0.8. Now, there are limits that fail to exist. So you can be given a function to find its limit, but in truth is that the limit of that function does not exist. So it's good to be able to tell from earlier on which function, what kind of function, which types of functions have their limits failing to exist. And there are 3 behaviors. The first one is what goes contrary to what we have seen. We have seen that for us to say that the limit exists, or for the limit of a function to exist here, is that the behavior from the right should be the same as the behavior from the left. So if it goes contrary to that, so behavior that differs, so we can say behavior that differs from right to left, from right and left. So behavior that differs from right and left. And again, I will just graphically look at this in terms of function. So we have f of x is equals to x over. So we look at the limit of this function. So that is our function. And then we look for the limit as x tends towards 0. So again, we are supposed to pick values that are very close to 0, and our function is. So this is what we are working on. So what this implies is simply the absolute value. And remember, the absolute value, it implies you, in layman's term, it implies you simply just ignore the negative sign. So if you're talking about 3 as an absolute value, that implies that either that was negative 3 or it was positive 3. So then, without looking at the absoluteness of this function, we can say that we can look at it in terms of we are talking about a constant over the same constant. So it implies that instead of picking values that are very close to 0, for example, 0.00001 over 0.00001 will still give us 1. Whether it is negative or positive, it will give us 1. So we can actually just pick values, integral values from the left to represent values that are very close to 0, and again integral values from the right to represent the values that are very close to 0 from the left. So that implies that we can use x, f of x. Here we can use -4, -3, -2, -1, 0. Then this other side we use 1, 2, 3, and 4. So then when x is -4, this will give us -1. So that is also -1, -1, -1. At this point, this function is not defined. And then when x is 1, this will give us 1, this will give us 1, 1, 1. If we draw this graph, this side will have -1, -2, -3, -4. This is 0. Of course, this is our y coordinate. This is our f of x is here. That's our x. This is 1, 2, 3, and 4. So we have -1 at this point. We have 1 at that point. Then we have -2. We have 0.2 up that side. So these positive values are giving us all of them 1, 1, 1, and 1. These are the side. They're giving us -1. This is -1, -1, and -1. Remember, our interest is we are looking for the limit as x tends towards 0. So our direction is towards 0. So that implies that, because it is at this point that x is equals to 0, and also at this point where x is equals to 0. So the function is not defined at this particular point, and the function is also not defined at this other side. So, and then the direction this side will be. So what we see here is that the behavior from the right is totally different from the behavior from the left. So from the left, f of x is tending towards 1. From the right, f of x is tending towards 1. But from the left, f of x is tending towards a -1. So in that case, the behavior from the right is actually different from the behavior from the left. So in that case, the limit of this function does not exist. So we go to the second behavior that specifies or is an indication that the limit of the function fails to exist, and this is unbounded behavior. Unbounded behavior. So unbounded behavior is where the function either increases without bound or decreases without a bound. So again, here we'll use a function. Limit will be as x tends towards 0 of, let's say, 1 over x squared. So if you pick 1 over x squared, the negative side and will be represented by the positive side, because a negative squared is equally like -2 squared is the same as 2 squared, which is 4. And then we're talking about x tending towards 0. So we don't need to pick many values. We can make a conclusion from this. So this x is tending towards 0. So this is 0. We pick values of x. We can pick them in terms of 10, multiples of 10. So we can start with 100, and then we go to 10, and then we go to 1 over 10, which is 0.1. We go to 1 over 100, which is 0.01. We go to 1 over 1,000, which is 0.000. 0001. Okay. And then, so these are the values of x. These are the values of f of x. So when x is 100, so that would give us 1 over 10,000. So that would give us 0. That is 1 over and then when x is 10, so that will give us 1 over 100. So 1 over 100 will give us 0.01, and then when x is 0.1, so that is 1 over 10, so that would give us 100. When it's 1 over 100 or 0.01, that would give us 10. When it's this, it will give us this is not the closest that we are to 0. We are still very far from 0, but we can be able to make a conclusion that as x is tending towards 0, that is movement downwards, f of x on the other hand is just increasing. So it will keep increasing, and there's no particular point where we'll say that this is the closest we are to 0. So f of x now is giving us this kind of, or is tending towards this value. You can see clearly that it's just increasing and increasing without bound. So that's basically what we mean by unbounded behavior. So again, for this function, you cannot say that there's a particular value that f of x is tending towards. So the limit fails to exist. And then we go to the last behavior. So the last behavior is oscillating behavior. So oscillating behavior is where values of f of x are oscillating or are moving about some 2 or 3 values. So we have oscillating and oscillating behavior. So oscillating behavior is the third behavior of a limit that fails to exist. So here again we'll use a function. So limit as x tends towards 0, sine of 1 over x. Then we pick values. So we have x, we have f of x. We'll pick 2 over pi, 2 over 3 pi, 2 over 5 pi, 2 over 7 pi, 2 over 9 pi. So of course, from this trend, we can actually see that these ones are clearly moving towards 0 by the ratio of the 2. So these ones are moving towards, that is the ratio of the denominator to the numerator. The numerator is constant, the denominator is growing, so that implies definitely this is a trend that is moving towards 0. So when 2 over pi, we work it out here, it will give us 1. This will give us -1, 1, -1, 1. So you can see that there is no particular one value. You cannot talk about either the function tending towards 1 or the function tending towards -1. It's playing about these two values, 1, -1, 1, -1. So that implies that, again, the limit of this function fails to exist. So next we go to analytical approach to limits. So the first one was graphical and numerical approach to limits. So for all those limits of all those functions that we have done before, or the ones that we have done a few minutes ago, all of them, if you draw the graph, it will have a hole at a particular point, which implies that the function, of course, is not defined at that particular point. So we go to analytical approach to limits. Analytical approach to limits. And here we use the properties of limits. So we use properties of limits to help us find the limits of different functions. So for these properties, we can let B and C to be real numbers. N a positive integer, and F, G, and H to be functions. So we have b and c as real numbers, n a positive integer, and f, g, and h to be functions. So the first property, is that the limit of a constant, is a constant itself. So that implies that if you have limit as x tends towards c of b, remember we said b was a real number, this would just be b. Example here, you have limit as x tends towards 2 of 5, the answer is 5. Or you have limit as x tends towards negative 3 of negative 7. This will just give us negative 7. The second property is that the limit as x tends towards c of x is c. So the limit as x tends towards c of x is c. So then, example, limit as x tends towards, let's say, 3 of x, this will be 3. Limit as x tends towards negative 1 of x, this will be negative 1. Then the third rule is the constant multiple, or multiple where we have a constant multiplying our function, or our function pre-multiplied by a constant. So if our constant here is b, so we have limit as x tends towards c of b f of x. So our function is f of x, and we can see that our function is being pre-multiplied by b. So if this is the case, this is the same as getting the limit first. So you get the limit of the function first, and then you pre-multiply by the constant. So examples here we can have limit as x tends towards, let's say, 5 of 2x. So this would be 2 times limit as x tends towards 5 of x. So that would give us 2 times 5, which would give us our answer as 10. So that would give us our answer as 10. Then we go to the third function, to the third property. So that's a sum. Third property. This is third or fourth. I think it's a fourth. So this is sum or difference. Sum or difference. So where you have a sum or a difference of two or more functions. So you have a limit. If you are supposed to get the limit as x tends towards c of f of x plus g of x plus h of x plus or minus, so that you can take care of the two signs. So this would imply you get the limit. So your function is a combination of, is a sum or difference of many functions. So this is the same as getting limit as x tends towards c of f of x plus, so you get the individual limits of each function and then get the sum or the difference of the limits. So this would give you again limit as x tends towards c of, h of x. Okay, so an example here, we have, we're supposed to get limit as x tends towards 2 of 3x plus 1. So this would be limit as x tends towards 2 of 3x plus limit as x tends towards 2 of 1. So this one would give us 3 limit, so that would be 3 times 2 and then plus limit, so this would give us 1, so that would give us 7. That is 6 plus 1. If you're given a limit, so this is the first example, this is the second example. You're given limit as x tends towards a negative 3 of 4x minus 2. So again, the same process, get the limit of the first and the limit of the second, then our difference of the limits. So this would give us 4 times negative 3 minus 2, which would give us negative 14. Okay, so that is sum and difference. We can go to the power rule. So power rule, this is another rule of limits, and here if you're given the limit as x tends towards c of our function being raised to a certain power, remember we said n was a positive integer, so this is the same as getting the limit as x tends towards c of the function first, and then you power the limit. So for example, if you're supposed to get limit as x tends towards 2 of x squared or x cubed, this would be the same as getting the limit first as x tends towards 2 of x, and then so this would give us 2 cubed, which would give us 8. And then after the power rule we have the root rule. So limit here, limit as x tends towards c of f of x. So where you're supposed to get the root. So this is the same as getting so this should be the other way around. What I'm writing now is what I should have written first. So it should be you're given the limit as x tends towards c of the root of your function, and that is the same as getting limit as x tends towards c of f of x, and then you get the root. So you get the limit first, find the root of the limit. Example, you have limit a limit as x tends towards 6 of root of 2x plus 4. So this is the same as getting the root of limit of 2x plus 4 as x tends towards 6, which gives us our answer is square root of 16, which will give us 4. So that gives us 4 is our answer there. Then we go to the next rule, so the quotient rule. Quotient rule. And for the quotient rule, this is where you're supposed to get the limit of a quotient as x tends towards c of f of x over g of x, and this is the same as getting the limit of each function as x tends towards c. So you get the limit of f of x, the first function, and then you find the quotient of that limit with the second limit. But there's a rider here. So provided a limit as x tends towards c of g of x is not equal to 0. So we'll later on see what happens if the limit of the denominator is equals to 0. What is it that you're supposed to do? So for now we just concentrate on the fact that we are supposed to get limits of functions that are a quotient, and we are supposed to use that fact. So example, you're given limit as x tends towards 2, 3x plus 5 over 2x, 3x plus 1. You can use this one. 4x minus 5, 3x plus 1 over 4x minus 1. So we get the limit of the upper function, get the limit of the lower function, and then we find the quotient of the two limits. So this will give us limit as x tends towards 2 of this, so that would give us 7. And then our limit as x tends towards 2 over the lower one, that would give us 3. So this is 6 plus 1, that should give us 7 for true. Oh, okay, so the difference. And then this one would give us 8 minus 5, that would give us 3. So second example to this is that if you're given limit as x tends towards negative 7 of x plus 4 over 2x plus 10, so that would give us 3, negative 3 rather, and then this would give us negative 4. So that implies that our limit there is 3 over 4. There is a note, so we can note something. So we go back to that rider where the denominator limit should not be equal to 0. So if, okay, the quotient rule cannot be used if the denominator limit is 0. Limit is 0. So what happens is that so instead we seek for a possibility that a factor of the numerator can be cancelled by a factor of the denominator. So once you have established that the denominator limit is 0, what you're supposed to do is that you factor the functions that you have, or maybe one of them is a factor of the other function, and then in that case that implies that you can cancel out what is common or what is a factor for both of them, and then you work out the limit as we have seen before, or as we have talked about previously in the quotient rule. So for example, you're given limit as x tends towards 4 of x squared minus 6x plus 8 over x minus 4. So x minus 4 most definitely is a limit of, is a factor of x squared minus 6x plus 8. So you use any method that you can factor out. You can use factorization method and get what this is, or you can choose to do a division. That is x minus 4, x squared minus 6x plus 8. This is faster and easier, so this would give us x squared, and then this would be minus. So this would give us negative 2x plus 8, negative 2x plus 8, this would be minus 2, so that would give us negative 2x, and then this would give us a positive 8. So then in that case we have a limit as x tends towards 4, x squared minus 6x, we are saying is x minus 4 into x minus 2 over this x minus 4. So in that case these two cancel. So we are just simply supposed to get the limit as x tends towards 4 of x minus 2, which now will give us our answer s 2. So whereas at this point the denominator limit was 0, and actually this was giving us an indeterminate form where we have 0 over 0. So there was no way we were going to it would have been easy to just conclude that the limit of this function that does not exist, but in truth it does exist. So we look for factors before you make that conclusion. You look for factors between the two. There's some circumstances where you can actually go ahead and look for factors, but still the limit of that function will fail to exist. I think we can look at such a scenario. So we have x squared minus 3x minus 2, 8. So we are getting the limit as x tends towards -1 of this function. X squared minus 6x minus 7. So the function, of course, is indeterminate if you work with it direct. So this will give us 0, and then this one will also give us 0. This one will not give us 0, but this one will give us 0. So the denominator limit is going to be 0, because this is going to be 1 plus 6 minus 7. So that will give us 0. So in this case, we have our function as x minus 7. So that is limit as x tends towards -1, x minus 7 into x plus 4 over x minus 7 into x plus 1. So yeah, you have factored out, you have the factors. This one is cancelled with this one, yeah, but still you can see that we'll have this one will give us -1 plus 4, yes, which will give us 3, but this one will still give us 0. So this function is not, so limit fails to exist. So limit fails to exist, or limit does not exist, either of the two. Okay. We go to the next, rationalizing technique of limits. So this is also a situation whereby you have a quotient more often than not, and then the denominator limit is actually 0, but there is no relation between what you have as your denominator and what you have as your numerator. But if you look at the function, you have a third, or you have an irrational part of it. So for example, if you're given limit as x tends towards 0 of x plus 4 root minus 2 over x. So you can see that's indeterminate or indeterminate, and then there's no relation, there's no factor that is shared by the two. So generally in such cases we rationalize the numerator. So we multiply by the conjugate, so that would be x plus 4 plus 2, and whatever we do to the numerator we do to the denominator. So this will give us limit as x tends towards 0. That would give us x plus 4, and then that would give us minus 4, and then this will give us x into root of x plus 4 plus 2. So then this will give us limit as x tends towards 0. That would give us x. Yeah, that x will cancel with that x, so that would give us 1 over. So this will be 1 over root of x plus 4 plus 2. And then x is tending towards 0, so that would give us 1 over 4. 1 over 4 is what we have there as our answer. We look at a second example to this. We have limit as x tends towards 3, root of x plus 1 minus 2 over x minus 3. So we do the same again. We multiply by the conjugate of the numerator. So we multiply by root of x plus 1 plus 2. Whatever we do to the numerator, we do to the denominator. So then this will give us limit as x tends towards 3. That will give us x plus 1, and then that will give us minus 4 over, this will be x minus 3, root of x plus 1 plus 2. Plus 2. Okay, so this is 3. This is limit as x tends towards 3. So this will give us x minus 3, which will cancel with what we have down there. So we'll have 1 over root of x plus 1 plus 2. So this will give us again 1 over 4. Okay. So next we go to limits of trigonometric functions. So limits of trigonometric functions. And the limit as x tends towards c of sine x is sine c. Our limit as x tends towards c of cos x is cos c. And limit as x tends towards c of tan x is tan c. And their reciprocals also apply here. So limit as x tends towards c of cosec x is cosec. C is basically short for cosec. And then a limit as x tends towards c of sec x is sec c. And then the last one, limit as x tends towards c of cot x is cot c. So those are limits of trigonometric functions. We can do a few examples on that. Limit as x tends towards pi over 4 of sine 2x. So this will be a sine of 2 pi over 4. So pi is 180. That would imply that we are looking for sine of 90. And then our second example, limit as x tends towards 3 over 4 pi tan x. So this is tan of 3 over 4 pi. So 3 over 4, I guess that is 135. That is 45 times 3, 135, and that should give us -1. And then our limit as x tends towards pi over 4 of sec x. This is the same as sec pi over 4. And then we know that sec is 1 over cos. So this is the same as 1 over cos of pi over 4, which should give us 1.4142. And then we have the special trigonometric functions, trigonometric limit theorems. So special trigonometric limit theorem. And the first one, we'll just talk about two. A limit as x tends towards 0 of sine x over x is 1. And the second one is limit as x tends towards 0, 1 minus cos x over x is 0. Some authors express this as, some authors express it in terms of limit as x tends towards 0, cos x minus 1 over x, and it is also 0. So if you come across it, it should not confuse you. The background of these two special limits that does not really concern us, but what you need to do is you must know them, so that when you're given a limit that you're supposed to find, you're given a function, you're supposed to find its limit, and it has trigonometric functions, you might be called upon, or it might be expected of you to use those two special functions. So the first one are examples now. So examples, the first one is limit as x tends towards 0 of sine x over 3x. So this looks like our first special limit, but it's not really the same. There's some alternation there. So then we know that we must use them as they are. So what we'll do here for this one is that we'll simply just need to factor out the 1 over 3 so that we have our special limit intact. So in that case, again, now from rules of limits, that will give us a third limit as x tends towards 0 of sine x over x. And this will give us a third times 1. Remember, the limit as x tends towards 0 of sine x over x is 1. So that would give us a third times 1, which will give us a third. Second example, a limit as x tends towards 0 of sine 4x over 4. So same thing again, close to our first special limit, but really not the one. So, and remember that this is an angle, and that makes it composite, as in it's not something that we can break. So we can only play about by the denominator. So, so that we take care of that, we'll have limit as x tends towards 0. We introduce, so by multiplying by 4 over 4, literally it means that we have done nothing much to the function. So whatever you do, you should not change the meaning of that function, nor should you change the value of the function that you're given. So basically that's what we've done. We've multiplied by 4 over 4, which is ideally just 1, and it is of no consequence to our, no, it's of no really value consequence to our function. So this will be limit as x tends towards 0 using rules of limit. So that should be 4, and then we have sine 4x over 4x. So this one will be 1. So this would be 4 times 1. So maybe just to mention something about that first special limit. So we've said that first special limit is a limit as x tends towards 0 of sine x over x. It doesn't imply that this, what we have here, has to be x. X is general. So the deeper meaning behind it is that whatever you have here should be exactly the same as what you have here. So if you have 2y here, if it's y, it should be y. If it's z, it should be z and z. If it's 2y, it should be 2y. If it's 7z, it should be 7z. Okay. So limits, third example on this, limit as x tends towards 0, tan of 4x over 7x. So this one actually has no direct, from face value it has no direct relation, or you cannot be able to relate the special limits that we've talked about and this one. But in the real sense, we know that a tan x is sine x over cos x. So this implies that this is a limit as x tends towards 0, sine x, sine 4x rather, over cos 4x times 1 over 7x. Okay. So which we can say, we can we play with this so that it factors, or it favors what we want to do, or we direct it towards using the special limits. So this would give us over 1 over cos 4x. So from rules of limits, our product I think we talked about product rule. If we didn't, product rule basically where you are supposed to get the limit of a function that is a product of two functions. You get the limit of the first function, and then the limit of the second function, and then you get the product of the two limits. So then this would give us limit as x tends towards 0, sine of 4x over 7x times limit as x tends towards 0, 1 over cos of 4x. Then here again, so that we sort this out, it implies that we will have to introduce some factor here. So we multiply by 4 over 4 again. So if you multiply by 4 over 4, that would give us 4 sine, so that is 4 over 7 sine 4x over 4x times 1 times limit as x tends towards 0, 1 over cos 0. So then this will give us our answer. This will be 1, this will be 1, this will be 4 over 7. So our answer is 4 over 7. So then we move to one-sided limits. One-sided limits. One-sided limits. And here we have either the right-hand limit or the left-hand limit. So when do we say that L is a right-hand limit, and when do we say that L is a left-hand limit? So here, given if you're given the interval SC, so you have the interval SC where f is defined, given SC, and f is defined on that. So f is defined in all these from this is an open interval, so that implies A is not inclusive, C is not inclusive, but for all the values that fall between A and C, our function f is defined. So if we are talking about this, and then L tends towards, or f of x tends towards L as x value tends towards A from the right. So they're tending towards A from the right. So given SC, f is defined, and given, let me write it in a different way. If f is defined, so if f is defined on the interval, if f is defined on the interval SC, I immediately to the right of A. So that is when we have a right-hand limit. For the left-hand limit, so f will be defined, but this time on the interval CA, and then it will be immediately to the left of A. So immediately to the left of A. I can use an example here to maybe make it clearer. So if we looked, there's a function that we did look at that we said that its limit fails to exist because the behavior from the left is different from the behavior from the right. And that was the function. We were getting the limit as x tends towards 0 of x over absolute value of x. And we picked integral values to represent the values that were very close to x from both sides. So we had x and f of x, and here we had our x being equal to 0, and we said that the function is not defined at that point, but on this side we picked integral values. We can pick from -3, let's say, -2 and -1, and this side again we pick 3, 2 and 1. So this other side, what we saw was that all these were giving us -1, this side they're all giving us positive 1. And if we draw this graph, we actually did draw it then. So we sketched it. So if we sketch this graph, we'll have these values tending towards, so these positive values, and then these are the negative values, -3, -2, -1, 1, 2, and 3. So the behavior from this side is that. This side again, the function is not defined at that point, but these ones are tending towards this, that side. So then this is an example of a function that has both the right hand limit and the left hand limit. So one is our right hand limit, because we are talking about values that f is defined. Our point of our c here is 0. So we are talking about c being 0, AC. Our interval is AC, where our a is 0. Or we can use AB, whichever. You can even use our interval AB. For example, if we use our interval AB, just so that we don't confuse with the fact that we've been talking about limit as x tends towards c all through. So just to make it so that we don't confuse with the two. So let's say that our interval is AB instead, so from A to B. So then, and A is 0. So we have values of x that are defined and on the immediate right of A. So that gives us our right hand limit. On this other side, we will be talking about values that are on the immediate left of our A. So if, for example, now we are talking about this still being A, and then we pick an interval this side. So in this case, it would be the interval BA. So you would have again values of x tending towards A, but from the immediate left. So that implies we're picking values that are very close. This is our A, this is our A. So we are picking values that are very close here on the immediate left. These are what will give us the left hand limit. But for the right hand limit, we're picking values that are very close to 0 from the right. Okay, so these ones here, and we are finding that f is defined actually. So we are getting values for f of x, but they are tending towards this value 1. So our right hand limit is 1 and our left hand limit is -1. Then we go to limits at infinity. Limits at infinity. Limits at infinity. So we know we have negative infinity and we have positive infinity. If you look at limit as x tends towards 0, or 1 over x, this is something that we can make a conclusion of. X is tending towards 0. So, and then we have 1 over, x is tending towards infinity, sorry. We are looking at limits at infinity. So x is tending towards infinity, not 0. So x, positive infinity in this case. So that implies that x is just increasing and increasing and increasing without bound. And if x is increasing, the denominator is increasing and the numerator is constant, automatically that implies that the limit there is going to be 0. That would be a function, the answer will be tending towards 0. So then, when we are evaluating limits at infinity, we use that aspect of limits at infinity that we've just talked about, the fact that limit as x tends towards infinity of 1 over x is 0. This is a very important aspect of limits at infinity. So when we are evaluating limits at infinity, for example, limit as x tends towards infinity of 5x cubed minus 2x squared minus 1 over x cubed minus x plus 1, generally what we do is that we multiply by the highest degree of x. So we divide. So we divide everything by x to the highest degree. So the highest degree here is x cubed. So this will give us 5x cubed over x cubed minus 2x squared over x cubed minus, so this should be limit as x tends towards infinity minus 1 over x cubed all over, we have x cubed over x cubed minus x over x cubed plus 1 over x cubed. So then after that, we remember that this holds limit as x tends towards infinity of 1 over x is equals to 0. So this will give us 5. So this will be limit as x tends towards infinity. This will be 5 minus this will be 0 because it will give us 2 over 0. 2 over x. 2 over x limit, that's the same as 2 times 1 over x, which will give us 0. And then 1 over x cubed, again is 1 over x, limit 1 over x times 1 over x times 1 over x. We can look at it that way, and we know limit as x tends towards infinity of 1 over x is 0. So that will be another 0 over, this will give us 1. This will give us 0 from the same argument, and then this one also will give us 0. So that would give us our answer as 5 over 1, which is 5. Which is 5. Then we look at another example. So what about if involves a root? X square root of x squared plus 1 over x plus 1. So we do the same thing. So we divide by everywhere by that, but remember that this is a root, so that will give us limit as x tends towards infinity, x squared over x squared plus 1 over x squared over x. This is root of x squared, so that implies that we are dividing actually by x plus 1 over 1 over x. So this will give us 1 plus 0, which will give us 1. So limit as x tends towards infinity, 1 over 1 plus 1 over x. So again, that would give us 0. So that would give us our answer as 1. So this can be positive or negative because we are talking about root here. So this is 1. So this is actually root of 1 if we are to be keen. So this will give us plus or minus 1 because of that. Okay. So next, ideally, should be limits by definition, which is a more rigorous discussion on limits, but I'll leave that to you. I want to continue to move to the next, which is continuity. Continuity. And we say that a function is continuous. Okay, when you're drawing the graph of a function, of course, we get values for x and f of x, plot them, and come up with a graph. Now, we say that a function is not continuous if its graph has holes, has jumps, or breaks. So, to define continuity, generally it's better to look at it first from the angle of graphs that are not continuous, and then making a conclusion out of that. So, there are for basically three main ones, three main types of graphs that would show that a function is not continuous. It's not pros, as in the graph somehow has either a hole, a jump, or that kind of thing. So we have the three. So we'll draw these three. The first one, so this is our f of x, this is our x, and we have this kind of function. So we know that for this function we have our interval there, and this is our point C. So we can say that for this function f is not defined at C. So we can see that the function is not continuous. There is actually a hole. So implying that this function is not defined at this point as C. And then the second one is where we have so if you look at this function, the limit does exist. So the limit exists because the behavior from the left is the same, from the right is the same as the behavior from the right. So the function is just not defined at C, but limit of f at C exists. Okay. And then next we can have this kind of function so again we have our interval AB, and we have, this is our point C, that is our point C. So here the limit, we can see clearly the behavior from the right is different from the behavior from the left. So then here automatically or obviously the limit fails to exist. So the limit as x tends towards C does not exist. So as much as we can see that the function is defined at C, but the limit fails to exist. Then the third one, so we still, this is our f of x, and this is our x, so this is also our f of x. And then this is our x. So we still have our interval AB, and then we have our function. That is our point C. So again, the function is not defined, because if we insert the value of C, or we get the value of f of x at x equals to C, you can see it's giving us a totally different, this is the value that it is giving us. But if we pick values that are very close to C and very close to C, that is from the right, both the left and the right, it's giving us values that indicate that actually a limit exists, but the limit is not equal to f of C. So we can make that conclusion here. A limit exists, but is not equal to f of C. So these three scenarios actually come to bring to attention or come to help in defining what continuity is. So for a function to be continuous at a point, let's say P or C, a point C, let's say point C, the following conditions must be met. So the following conditions must be met. So the following conditions must be met. The first one, the function has to be defined at C. So f of x must be defined at C. The second one is that the limit must exist. So limit of f at x is equals to C must exist. And then the third one, the limit. So this limit as x tends towards C of f of x should be equal to f of A. So f of C rather, not f of A, should be f of C. So f of x is defined at C, which implies f of C is in existence. A limit of f at x exists, yeah. And then the third one, these two should be the same. So example, I will go to an example, and we are supposed to find, we are to investigate if the limit as x tends towards 0. We are supposed to investigate whether the function f of x is equals to x squared minus 1 is continuous at x is equals to 0. So we check if this function is continuous at x is equals to 0. So we must check, or we confirm, if the three exist. If they do exist, then it's true that that function is continuous. If any one of them, if it goes different from what these three conditions are, then the limit does not exist. So let's start with the first one. At x equals to 0, so we simply just get f of 0. So it's at 0 inside there. So f of 0 will give us 1. So f of 0 is 1. And then we get the limit. So limit as x tends towards 0 of f of x is going to be, so whichever way you look at it, you can choose to use factors, or you can choose to go direct. If you use factors, you'll have x plus 1 into x minus 1 over x minus 1. And then you'll have 0 plus 1, which will give you 1. If you go direct, that will still give you 1. And then the third one. So we check if the two are, first, they're in existence, f of A is in existence, condition number 1 is met. The second one, the limit exists, condition 2 is met. And then the last one, is it true that the limit is the same as f of 0? So the limit is 1 and f of 0 is 1. So we can see that actually the function is continuous at x is equals to 0. What about at x is equals to 1? So if you're talking about x is equals to 1, if we look at it in terms of at the point where x is equals to 1, so x is equals to 1, f of 1 not defined. But we can see that the limit will exist. The limit will exist because we'll have 1 plus 1, which will give us 2. So if we use the same, we look for a common factor. So then that will give us the limit existing, and the limit is 2. But f of 1 is going to be 0. So already from that we can see that that function is not continuous from that argument, or from what we have seen there. And then you can also be asked to indicate points where a certain function is continuous. So for example, where at what points is a function at what points is the function x plus 2 over x squared minus 3x minus 10 not continuous. So it can either be not continuous or discontinuous. Let me use discontinuous. So at what points is the function x plus 2 over x squared minus 3x minus 10 is discontinuous. So the obvious way we've seen a discontinuity coming about is when we have the denominator limit as 0, so or the denominator value as 0. So we only need to equate this to 0, and then we solve. So this will give us a point where this function is not is discontinuous. So that would give us x minus 5 or x minus 2x. Which one do we put here? Plus 2x, and then minus 5x minus 10. So that would give us x into x plus 2. This is x squared minus 5 into x plus 2. So x is equals to 5, x is equals to negative 2. So at those 2 points, that's where this function is discontinuous. So it's discontinuous at x is equals to 5, and it is also discontinuous at x is equals to positive 2. Then we move to the intermediate value theorem. Intermediate value theorem. Intermediate value theorem. This simply states that if you have a function f continuous on an interval AB, on a closed interval actually, so continuous on a closed interval AB, and then there is a number, we can call it k, a number k, between, there is a number k between, is it between, so there is a number k between, might not be the very correct word to use here, between f of a and f of b. So if f is continuous on the interval, the closed interval AB, and there is a number k between f of a and f of b, it implies that there exists a value c in our closed interval AB such that f of c is equals to k. Okay, so f of c is equals to k. So nothing really major that the intermediate value theorem is talking about. Okay, the first thing it says that you have a function. The function is defined. That implies that you can actually be able to come up with a graph. There are no gaps, there are no holes. This is our interval AB. This is B. And then if that is the situation, the function is defined in our closed interval AB. So it implies that at all points of x between a and b, we are able to find values for x, and actually can come up with, have come up with a graph for that. So if it so happens this is our f of a, this is our f of b, and this is our f of a. So if it so happens that there is a k, a number k in existence between, or that is there in between these two functions, or these two values of f of x, so that is f of a and f of b, it implies that automatically there is in existence a c such that f of c is k. Examples to illustrate this show that the equation x cubed minus 3x squared plus 1 is equals to 0 has a solution, or a 0, on the interval 0, 1. On the interval 0, 1. So basically what you're supposed to show is that between f of 0 and f of 1, there does exist a k. So if we can show that there is a k in between f of 0 and f of 1, then automatically it implies that there is a number. We need to show that there is a k in between f of 0 and f of 1. Once we show that between f of 0 and f of 1, there is a k, then automatically it implies that between 0 and 1, there is a value c there. So we get f of 0. So f of 0 will give us 1. And then f of 1 will give us negative 1. So that would be, negative 1. So we can see that f of 0 is greater than 0. F of negative 1 is less than 0. So if f of 0 is greater than 0 and this one is less than 0, actually that implies that there is a 0 that exists between f of 0 and f of 1. So if it does exist, it implies that there is a value c between 0 and 1. So therefore, there exists a c in 0, 1 such that f of c is equals to 0, because we have shown that there is a 0 between f of 0 and f of 1. So we can do the same for this other example, x squared minus 4x plus 3. So this is the first example. This is the second example. So x squared minus 4x plus 1. Again, our interval here is 2, 4. So we do the same thing. We have f of 2. F of 2 will give us, so that would be 4 plus 3, 7, 7 minus 8, negative 1. And then f of 4 will give us 16 minus 16 plus 3. 16, yeah. So this one again is less than 0. This one is greater than 0. So again, there is a 0 existing in between. So we can still make the same conclusion that there is a c that exists in between 2 and 3. Okay. So then we move to the next thing, and that is differentiation. Differentiation, and generally the derivative is simply expressed as or defined as the slope of a function at a particular point. Generally, we know that we get the slope or the gradient of a function using 2 points on the function that is given. So for example, if this is our function, so we have our point A here that has coordinates x, f of x, and we have our next point here, our B, that has coordinates x plus change in x. So this is change in x from here to here. This is change in x. So that is change in x, change in x. So that is change in x. Let's use this other one. And then, so b will be x plus change in x. And then that would be our x coordinate. And the y coordinate, we know that is always a function of the x coordinate at that point. So we know that if we have this line, so this is our A here. Okay. So if we have our line there, the gradient, if you draw that line, the gradient is going to be change in y over change in x. So m is going to be change in x over change in y, which will give us f of x plus change in x minus f of x over x plus change in x minus x, which will simply just give us change in x, because we are doing change in y over change in x. Now, this is a second. If we want to get the true value of the function, let's say, of the slope of this function at this, we'll be getting the derivative of that function. And to get the derivative of that function, if we pick values of change in x that are closer and closer to this point, we will be moving closer and closer to the correct value of the gradient at this particular point. So if you look at the relation between the two, we can say that when you are getting the derivative, we just put a limiting factor to the change in x of our slope. So dy over dx is limit as change in x tends towards 0 of our m. We are simply putting a limiting factor to our slope, which is this. So this is basically the definition for derivative, also expressed as derivative from first principle by the limiting process. So after that, we can look at some of the notations that we use. For derivative. So we have this first one that we've talked about, dy over dx, and then we have y bar. We have, so this is y bar. We have f bar of x. We have d of dx of our function f of x. And then we have, this is also another one, another notation that we can use. So all these are notations for derivative, but it's important to note that in talking about all these notations, we are talking about a function of x. So we are talking about, by virtue of y bar, we are literally saying that we are talking about a function y of x. So that does not imply that all derivatives will be of a function y that is defined at x, or a function or y a function of x. You can still have s is equals to 3t plus 2. So in this case, you'll be talking about ds over dt. You'll be talking about ds over dt. If you have v is equals to 3t squared plus 4t, you'd be talking about dv over dt. So again, the notations, of course, is dependent on what kind of function you're talking about. Okay, so let's look at derivatives from first principles. So derivatives from first principles. Also, I said this is the same as by the limiting factor. Or from first principles. All of them imply the same thing. So the first example is that we are supposed to get the derivative of the function y is, let's say, 4x plus 5. So from the definition, we see that we need to have f of x plus change in x and f of x, and then we simply insert in that definition and work with it. So our f of x here is, of course, 4x plus 5. Our f of x plus change in x is going to be, we insert, while we have x, we insert x plus change in x. So we'll have 4 into x plus change in x plus 5. So this will give us 4x plus 4 change in x plus 5. Then we can bring in our definition. So dy over dx is going to be limit as change in x tends towards 0 of our f of x plus change in x. So that is that over minus f of x. F of x is this one. So we are subtracting this one. That will give us minus 4x minus 5. So, and then over change in x. So this will give us our answer as limit as change in x tends towards 0. 4x, that will give us 4. Because change in x and change in x will also cancel. So 4x and 4x will go, 5 and 5 will go. We'll have 4 change in x over change in x. So that change in x will cancel. So that will give us 4. And then we know that the limit of a constant is a constant itself. So that would give us our answer as 4. Go to the second example. Second example, we have f of x is equals to 5x squared plus 2x minus 1. Again, we are supposed to find the limit of this, we are supposed to get the derivative of this function from first principles or by the limiting process. So again, we need f of x plus change in x. So this will give us 5 into x plus change in x squared plus 2 into x plus change in x minus 1. So if we open up this bracket, this will give us 5x squared plus 10x change in x plus 5 change in x squared plus 2x plus 2 change in x minus 1. And then we go to the definition. So this will give us limit as change in x tends towards 0. And then we have the whole of this, we subtract this. So 5x squared plus 10x change in x plus 5 change in x squared plus 2x plus 2 change in x minus 1. We are subtracting this, so that will give us minus 5x squared minus 2x plus 1 all over change in x. So this will give us limit as change in x tends towards 0. So 5x squared and 5x squared will go. We'll have 2x and 2x will go, 1 and 1 will go. So what remains, what will remain, this is plus 10. This should be plus 10. So plus 10. Yep. So this is what will remain, and this one and that one. So the rest will all go. All of them have change in x. You can factor out that. So that would give us 10x plus 5 change in x plus 2 over change in x. So change in x and change in x will cancel. That would give us limit as change in x tends towards 0. 10x plus 5 change in x plus 2. And then change in x is tending towards 0. This implies that will be 0. So our answer is simply 10x plus 2. Another example, we try to take examples from different types of functions. So the next we can take maybe a fraction. So limit as x tends towards, still talking about a limit. So f of x, we are given f of x as, let's say, x over x plus 2. So we'll have f of x as that. Then f of x plus change in x will be x plus change in x over x plus change in x plus 2. So then we'll have dy over dx as limit as change in x tends towards 0. This will be x plus change in x over x plus change in x plus 2 minus x over x plus 2. Then, as usual, the way we deal with fractions, we find the LCM. So that would give us x. The only thing is that we are supposed to put over, all over change in x. So all over change in x is the same as multiplying by 1 over change in x. So I can write it here, over change in x. So we can put it here. That's the same as putting it down there. And then our LCM is going to be x plus change in x plus 2. And then into x plus 2. Then as usual, this will give us x plus change in x into x plus 2 minus x into x plus change in x plus 2. So that one you can even just write it as x plus change in x plus 2. And then this will give us limit as change in x tends towards 0. So this will give us x squared, x squared plus 2x plus x change in x plus 2 change in x minus x squared minus x change in x minus 2x over change in x, x plus change in x plus 2 x plus 2. So then x squared will go, 2x will go, x change in x, x change in x and x change in x will go. So what remains here is 2 change in x, 2 change in x, change in x and change in x will cancel. So this will give us limit as change in x tends towards 0, 1 over x plus change in x, x plus change in x plus 2 into x plus 2. And then x is change in x is tending towards 0, so that will be 0. So that will be x plus 2 into x plus 2, which will give us 1 over x plus 2 squared. 1 over x plus 2 squared. And then we equally can do one that has root. So we have f of x is equals to root of 6x minus 1. So again, we're supposed to find the derivative of this function from first principles. So we'll have f of x plus change in x, and this will be root of 6 into x plus change in x minus 1, and then we go to dy over dx is limit as change in x tends towards 0 of f of x plus change in x. So this is root of 6x plus 6 change in x minus 1 minus root of 6x minus 1 over change in x. So as we rationalize here, so we'll multiply. So we have 6x plus 6 change in x minus 1 minus root of 6x minus 1, we multiply by root of 6x plus 6 change in x minus 1 plus root of 6x minus 1 over change in x. Then we also multiply by that, so that would give us 6x plus 6 change in x minus 1 plus root of 6x minus 1. So this will give us limit as change in x tends towards 0. So that would give us 6x plus 6 change in x minus 1, and then minus 6x plus 1 for that one. And then this will give us change in x, root of 6x plus 6 change in x minus 1 plus root of 6x minus 1. So then everything else there will go apart from 6 change in x. Change in x will cancel with that change in x down, and then that will give us a limit as change in x tends towards 0 of 1 over root of 6x plus 6 change in x minus 1 plus root of 6x minus 1. Then change in x is tending towards 0, so that would give us our answer as 1 over 2 root 6x minus 1. So that is all about differentiation from first principles. We go to rules of differentiation. Rules of differentiation. Rules of differentiation. So rules of differentiation. And the first rule is that the derivative of a constant is 0. So derivative of a constant I is 0. So if you're given f of x is equals to 5, f bar of x is going to be 0. You're given y is equals to negative 3, dy over dx is going to be 0. Second rule is the power rule. This is the power rule. So for the power rule, if you're given y as x raised to power n, dy over dx is going to be n x n minus 1. So you should be able to find out how this comes to be. So you can pick any text on calculus, and it's important for you to see how this comes to be. But for now, we'll just concentrate on examples. And so we have, you're given, for example, so we go to examples. For example, the first one, a, y is x cubed. You know that, of course, dy over dx will be 3x squared. So y is 4x raised to power 4, dy over dx will be 16x raised to power 16x raised to power 3. So if you have x, y is x raised to power negative 4, dy over dx will be negative 4x raised to power negative 5. And maybe just one more example on y is x raised to power a third. You know, you'll have dy over dx as a third x raised to power negative 2 over 3. So that is the power rule. We go to the next rule. Sum or difference, derivative of sum or difference. So that is number 3. Sum or difference. So for example, you have, so if you have a function that is a sum or difference of many of other functions, so dy over dx is going to be 4x cubed plus 2. That's a constant. The derivative of a constant, you've said, is 0. And if you have y is equals to 1 over 5 x cubed plus 2x squared plus 7x, we do the same. This will give us 3 over 5 x squared plus 4x plus 7. So one last example on this. You're given f of t as 4 over t plus 1 over 6 t cubed plus 8 over t raised to power 5. So in such cases, you have to make this to be part of your numerator. So that would be 4t raised to power negative 1. So that's 4t raised to power negative 1 plus 1 over 6 t raised to power negative 3 plus 8 t raised to power negative 5. So once you have it there as that, you can comfortably find the derivative. This will give us negative 4 t raised to power negative 2 minus, this will give us a half t raised to power negative 4 minus 40 t raised to power negative 6. Okay. So that is sum or difference. We go to the next. The product rule. So product rule. And product rule is used when you're supposed to get the function, the derivative of a function that is a product of two functions. So maybe we give it an introduction. So we let f and g be differential. So f and g are functions. So these are two functions that they be differentiable at x, or they be differentiable functions of x. So that implies that the product of the two is also differentiable. Is also differentiable is also a differentiable function of x, and the derivative of fg is going to be f bar x gx plus fx g bar x. So the derivative of the product of f and g is going to be f bar x gx plus fx g bar. So you get the derivative of the first function multiplied by the second function as it is, and then you add to now the first case you took the derivative of the first function, the second case you take the first function as it is, but you get the derivative of the second, or equivalently. So if you have u as your f of x and you have v as your g of x, then the rule takes the form. So rule becomes the derivative of the product of uv will be u bar v plus v bar u. So u bar v plus v bar u. So we can go to examples. So examples. So you're given y as x raised to power a third into 2x minus 1. You're supposed to find the derivative of those two functions, and you can see the derivative of this function, which is a product of two functions. So you let your u to be your first function, which is x raised to power third, and you let your second function v to be 2x minus 1. So then you get u bar. U bar is going to be the derivative of your function. So this will give us a third, x raised to power negative 2 over 3. And then you get v bar. V bar is going to be 2. So then you follow